In today's lesson, we're going to learn about logarithmic equations. For logarithmic equations, there are two primary approaches. We're going to start with approach number one. That's when you have logs on only one side of your equation. The goal will be as follows. You're going to use the properties to condense to a single log all by itself. Then you'll do a rewrite of the equation in exponential form. So example number 4 uses this approach. As we're C, we are down to one log on the left side. Nothing is multiplied, divided, added, or subtracted to it, so we have it all by itself. This is when we go ahead and do a rewrite. Rewriting it from B-N-E, so our Benet, to B-E-N. I'll take the B, the E, and equal it to my N here. Just remembering how to rewrite it. From here, think about your rules of solving equations. We'll do the exponent first, giving me 2 to the power of 3 being 8, and keeping the right side equal to 7x minus 6. Goal is to get x by itself, so we have to add 6 to each side, getting you 14 equaling 7x. Divide by 7, and we get our final answer of x equals 2. Before we finish this problem, I just want to bring your attention to a note we have right underneath this problem. The note says when solving logs, always check for extraneous solutions. Two cases where a log can be extraneous. Let's go ahead and put an example in. The base of the log must be positive. So that's when talking about the log here, we had log base 2, for example. And we'll just put an x variable to hold it. As long as that bottom base number is positive, you don't have an extraneous case for that specific reason. Another specific reason, that's why it says and, bolded and underlined, that logs can be extraneous, is when the simplified number inside your log is positive. That must be the case or else it's extraneous. So let's check that in this problem here. So for my check, you can do it on the side here. I'm going to take my x value and replace it into x everywhere in my original problem. Go back to the very original problem, the one that was given to you on the piece of paper when plugging in. So instead of log base 2 of 7x minus 6, I have log base 2 of 7 times 2 minus 6. I go ahead and solve the inside of this down to get log base 2 equaling 14 minus 6 equaling 3, for instance, inside the parentheses 14 minus 6, and I get log base 2 of 8. Because that is a positive number inside, and because the base on my log is positive, I have no extraneous solution when x is 2. So let's put that example down here below, just from above. I had log base 2 of 8, specifically pointing to that the inside of the log must simplify down to a whole number that's positive. Let's look at approach number 2. Approach number 2 happens when you have logs on both sides of your equation. The goal is then to condense both sides to make sure the log is all alone by itself, and to make sure to set the inside of the log equal to each other to solve for x. So as you see, for example number 5, we're going to use the second approach because I have a log on both sides. That was not the case for example 4. My logs must be all alone. I'm going to let you know that on the right side, the log is all alone because it's just log base 6 of 16. But over here on my right side, I have 2 times the log base 6 of x. So I have to move this 2. And the only way to move that 2 is with the properties of my logs, of how to condense them. When I have a number multiplied in front of my log, I can bring it up as an exponent inside of my log. So now I'll have log base 6 of x, but squared as the exponent. Now my log is all alone, nothing multiplied, divided, added, or subtracted outside of the log. I can go ahead and set the insides of my log equal. So that will go ahead and give me x squared equals 16. Just setting the inside of the logs equal to each other. In order to get rid of an x squared, we have to take the square root and think back to your Algebra 2 and Algebra 1 class, because when you yourself take the square root of any equation, or an even root specifically of any equation, you have to add a plus minus. Time to check for those extraneous solutions. So our check number 1 will start with the positive 4, plugging it into our original problem. So the original problem has the 2 in front. Make sure you keep it the original problem you are plugging in. Okay, check the bases, they are positive. Check the insides of the logs, they are positive numbers. So 4 is good to go. Let's go ahead and check negative 4. When I plug into the original problem, so the one you didn't even touch that you were given in the beginning, you're replacing it with what we just solved for. So for instance, we solved for a positive 4. That's what I plugged in for the first one, and saw that no base and no inside of a log was negative. I plugged in a negative 4 now. No base is negative here. But take a look at why is this an extraneous case. Specifically, because of what I'm pointing to now here, the negative 4 solo whole number inside my log that's negative. That can never be evaluated, never happen. We can only have simplified whole numbers that are positive inside of our log. So this is why it is extraneous here. The sole reason, and that's anywhere it appears, doesn't have to be every single log. As you saw, because the right side was a positive log, it's anytime any of the logs you replace comes out to a negative whole number inside the log. So the only answer I can choose here is going to be positive 4. You cannot include negative 4 as an answer. That answer is extraneous. Let's try example number 6. As you see, we're going to use approach number 1 because we have logs on only one side of the equation. What I have to do extra is make sure I condense it down to one log. Because the logs are added, we use our property that we then multiply the terms inside of our log. So that would be x plus 3 multiplied by the x plus 4 in my second log to combine them. And it equals 1. I now go ahead and do a rewrite here. So I'm going to have b and e, and need to rewrite it as b, then e, then n. So my b will be 6. My exponent will be 1. So that's a base of 6, exponent of 1. And it will equal everything inside of my log. That's how I rewrite it. Now I go ahead and solve. 6 to the power of 1 is 6. And then over here, 2 parentheses multiplied to each other, we got to FOIL or double distribute. So I'll go ahead and multiply x to both x and 4, getting me x squared plus 4x. And then I'll go ahead and multiply 3x and 3 times 4, getting me 3x plus 12. I will combine all like terms on both sides. So I see 2 numbers together. And I see 2 x terms on the same side that I'll combine with the same operation. But I had to do negative 6 because I had to move it to the opposite side. That gets me 0 equals x squared plus 7x, combining those two together on the same side. And then taking 12 with the 6 from the other side to make 6 over here on the right. That's a quadratic, so you know the deal. We have to factor. I think about for factors what multiplies to 6 and adds to 7, and that will be 6 and 1. Because on my x squared, I have just a 1 number in front of it, 1 coefficient. I can factor the shortcut method. X plus 6, x plus 1. I set each of those equal to 0, splitting them up so that way I'm able to solve each one and getting 2 values for x is my answer. Subtracting 6 gets me a negative 6 for this 0 for x. And over here, solving for this 0 for x gets me a negative 1. Don't forget, we got to check these. So when I check them, I plug them back into the very original problem. So I go ahead and look and write the original, just replacing every x value with negative 6 to start. Log base 6 of negative 6 plus 3 instead of x plus 3 here. Keep myself going here, plus log base 6, replacing this x again with negative 6, and then equaling it to 1. Okay, simplifying down my logs here, I'm going to go ahead and have log base 6, and then negative 6 plus 3 is going to give me negative 3. Next log, same thing, plus log base 6, negative 6 plus 4 gets me negative 2. Right away, this is an extraneous case because not only 1, but 2 are negative inside the log, which is why it's extraneous. But guess what? You only need one of those to be negative for this to be extraneous solution. So we had more than that, but you only need one whole number inside of any log in your original equation, negative, to make it extraneous. So I cannot include this answer. Let's cross it out. It's extraneous. Okay, let's check the next possible x value here. When I plug into my check, again, I'm plugging it into the original problem here. I have log base 6. Instead of x, I'm replacing it with negative 1 plus 3 in the parentheses stays. Then I add log base 6. And instead of x, I have negative 1 plus 4 in my parentheses, equaling to 1. I simplify those parentheses down to one single number. Negative 1 plus 3 is 2. Positive 2, so we're good there. And the next one simplifies down. Negative 1 plus 4, positive 3. Because the insides of my logs are a positive whole number, we're good there. And just double checking that my bases are positive. Everything is positive that needs to be. So that solution stands as an actual possible solution. Even though the solution itself is negative, when I plugged it into the original problem, I got a positive whole number simplified inside of my log, so that's okay. Example number 4. Same approach we just did, but now because we have subtraction, we'll actually be dividing these. So I'll take the natural log in front, and inside I'll have x plus 1 divided by what was in my second natural log, ln, which is x. And this will all equal 2. Once the logs are combined, we do a rewrite. Remember, the base on your natural log is always e, so that will be what we use in place of b. And then inside the log is going to be our n and e for our benet. Rewriting this, I get e as my base. The exponent is 2. And I set it equal to that whole x plus 1 over x. Solving for x, we have a fraction, so guess what? I have to multiply each side by the denominator. That gives me x to the times e squared. And it cancels out the x in the denominator on the right, giving me x plus 1. Again, goal is to get x by itself, so I want to get x terms, everything with an x, on one side of the equation. So that's why I'm going to subtract x on each side. That cancels out on the right, just leaving me 1. And I can leave the 1 on the right side because guess what? It does not have an x variable. On the left side, I cannot just subtract or cancel out these x's because one is multiplied to e squared and one is not. So I write them next to each other like neighbors. X times e squared minus x. Goal now here is on the left side, I want to take the GCF. I do that when I have moved all my terms with x onto one side, and how I move them is usually with addition or subtraction. So both terms have an x in common, so I can take out an x, leaving me with just e squared in my first term and a negative 1 in my second term. Still equals 1 for this problem. From here, it's x multiplied to the whole parentheses, so opposite of multiplication is division of that whole parentheses term. What I do to one side, I must do to the other. My x value here is going to come out to be this final answer of x equals 1 over e squared minus 1. And I leave it just like that. When checking for an answer with e in it, e is actually what we call Euler's number. It's going to be approximately 2.718. You can actually type that in a calculator and see that you get that decimal. So let's simplify this fraction down using that decimal. We'll just round to the nearest tenth. That's all we need. 2.7 squared minus 1. I'll do the exponent first, which still leaves me with 1 in the numerator. 7.29 minus 1 in the denominator. Combine the denominator to get 1 over 6.29. That's an ugly fraction, but I just need to know it comes out to be positive here, which is good. So I'm plugging in a positive number when I'm checking, so that's helpful to know. So in my check, I'm going to use that simplified number I just got to plug in everywhere I have x. So instead of ln x plus 1, I'm going to have ln 1 over 6.29 plus 1 here. Then I'll go ahead and subtract ln, again replacing that positive number inside, 1 over 6.29. And I'll equal it to 2 because that's my original problem. So before even solving this down, I know that this inside is going to be positive here because that's a positive fraction. Even though it's a decimal, it's still positive overall. Here I'm taking a positive number, so that's why it was beneficial to know that the answer was positive and adding 1. And guess what? Anytime I have a positive number and add 1, it's still positive. So therefore, this is an actual answer and it checks out. Remember that when you have E in your answer, you're really just looking for positive numbers inside of your log and making sure that your log has a positive number base. So that's as far as you need to go. I don't need to actually find the number inside of the log. Just got to make sure whatever is inside my log is positive. Last example here. What does it kind of look like? A quadratic. So I'm going to go ahead and quadratic this, aka factor this. How I'm going to do that is I'm going to go ahead and make a letter, I'll use A here, that's equivalent to what my variable is factoring here. And if you see my variable inside the square term, it's going to be factoring with ln x instead of just regular x. So I'll replace every time I have ln with a substitute letter a. So instead of ln x squared, I have a squared. Instead of minus 4 times ln x, I'll still keep the minus 4, but replace ln x with a. And then last but not least, I'm going to have negative 12 left over. No ln x on that term. So the only reason I'm doing this is because I saw this special case out front. Let's star it here, where I had ln x, the whole thing in parentheses squared. That's when I knew I had to replace that ln x with a variable to help factor. Now I can factor this thinking about what multiplies to negative 12 and adds to negative 4. That's going to go ahead and be a negative 6 and a positive 2. Because my coefficient is 1 in front of my variable term, I can factor the shortcut method. A minus 6 and a plus 2. And I'll break each one up, setting them equal to 0 here. A minus 6 equals 0, and a plus 2 equals 0. I subtract 2 on each side to get a equals negative 2. And over here, I'm going to add 6 on each side to get a equals positive 6. Now here's the deal. I'm going to go ahead and replace those a's back with what they're equivalent to that I made the equivalent in the beginning to ln x. So I replace the whole side of a with what it's equivalent to, ln x, and that's now equal to 6. Over here, I replace the whole term of a with ln x, and that is now equal to negative 2. Okay? My goal is to get x by itself in this problem, so it requires a rewrite of both of these answers. I take and write the base in on my natural log ln, which is going to be e. That's going to be my base. My number will be x, and my exponent will be 6 for this first one. So when I rewrite it, I get e to the power of 6 equals x. And now my x is by itself when I rewrote it from bne to ben. Same idea here. Again, I keep the base, which on my natural log is e, and will be my x, and my exponent will be negative 2. Doing a rewrite, I have the base e, exponent of negative 2, and set it equal to my number inside of my log, which is x here. Rewriting it as ben. Again, my answer here. We got to go ahead and check out that there's no negatives inside of my log. Remember, when we have e, we're just simply looking to see if it comes out to be positive. So when I do the first check here, remember e is about 2.718. So when I do 2.7 and I take it to the power of 6, that's definitely a positive number. So plugging it inside of my first log here, that's a positive number. Plugging it into my second log in place of x, again, leads to a positive. And that's all I need to know, that the inside of my natural log is positive, because guess what? We always know the base on natural log is positive. It's e. That decimal of 2.718 going on. But we just need to check that we're plugging in and getting a positive number. For our second one, before I plug it in to check with e, I'm going to go ahead and rewrite this, because remember, with a negative exponent, our rule is that to make it a positive exponent, I have to move it down across my fraction bar. So in this case, it's on the top of the fraction bar, so I got to move it to the denominator to make that the same base of e, but now a positive 2 exponent. This would be equivalent to approximately 1 over 2.7 to the power of 2 squared here. Remember, we did that last time with the calculator just to get an estimate of 1 over 7.29. You didn't even need to go that far because you could have figured that okay, 1 divided by any whole positive number is going to result in a decimal, but a positive decimal. So since that is positive, as long as when I plug it into my natural logs, it stays that way, I can go ahead and include that answer. So in place of x everywhere I have it in this problem, I'm going to go ahead and put that fraction in. You can use either the 1 over e squared, just knowing that it's positive. You can use the 1 over 7.29 if numbers help you a bit better. But just checking it out, it came out positive here because it's just the number itself that was a positive decimal. And same thing for the second ln natural log. I'm plugging in the positive number with nothing subtracted to it, so it stayed positive. So that's why just knowing the sign on it is going to give you the answer here. Just knowing that those are positive answers is going to help you solve and find out if inside the log comes out to a positive or negative.